The name of this section is the Central Limit Theorem. Now, what you're actually going to have to do here isn't all that much different from what we were doing in the last section. Here's an example of the kind of question you'd be asked in this section. The heights of all the flowers in a meadow are normally distributed with a mean of 15.5 inches and a standard deviation of 2.2 inches. You pick a random sample of 12 flowers out of all the flowers in the meadow. What's the probability that the average height of the flowers in your sample is over 17.5 inches? So we can write that like this. We want the P, the probability of X bar being greater than 17.5. So here the X bar stands for the average height of the flowers in the sample. This is a lot like an example from the last section, except instead of just talking about a flower, what's the probability that a randomly selected flower is over 17.5 inches tall? We're asking, what's the probability that these 12 flowers have an average height that's over 17.5 inches tall? Now remember the symbols we use. We use this Greek letter mu to stand for the population mean. And we use an X with a line over it, X bar, to stand for a sample mean. So mu would be the mean of the heights of all the flowers in the whole meadow. And X bar would be the mean of just those 12 flowers that you selected. Now, I'm going to show you how to go about answering this question. How do you solve a problem like this? But first, some background. If I said to a bunch of you guys, hey, everybody go out into the meadow and pick a sample of flowers. Measure those flowers that you picked and calculate the mean of the heights for the flowers in your sample. So if everybody goes out and randomly selects a dozen flowers, a different dozen flowers for each person, maybe one person might get 12 flowers of various heights, but their average, their sample mean, turns out to be 15.491 inches tall. Another person gets 12 flowers with a sample mean of 15.571 inches. Another person's sample has a mean of 15.864. Another person finds 12 flowers whose sample mean is 15.236. Another person's sample mean turns out to be 14.897. So each person has a different sample, a different group of 12 flowers with a different sample mean. So if you take several different samples from the same population and calculate the mean for some variable, in this case, the height of the flowers, but you calculate the mean for each sample is going to have its own mean. The X bar for that sample won't be quite the same as the X bar for some other sample. They'll differ from each other and from the mean for the whole population. The mean for the whole population, remember, was 15.5. So that's the average height of all the flowers in the whole meadow. But some of those groups of 12 had an average height that was a little more than that. Some of them had an average height that was a little less than that. They differed because of what's referred to as sampling error, which is the difference between a sample measure, like the mean for the sample, and the population measure, like the mean height for the whole population, due to the fact that the sample is not a perfect representation of the population. And error in this sense of the word doesn't refer to you made a mistake. It just means the difference between the actual value of something and the measured or estimated value. Okay, so here is the official statement of the central limit theorem that this section is named after. I'm going to read it to you, but then I'm going to tell you what it actually means and why it's important and what it's actually telling us. So it says, as the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. This distribution will have mean mu and standard deviation sigma divided by the square root of n. Okay, now I'm going to try to tell you what this actually means from a practical standpoint. It tells us three things. Number one, it tells us that the mean of all of those different sample means should be equal to the population mean. The mean of the x bars is mu. So if you took a bunch of different samples, calculated the mean for each of those samples, but then averaged those sample means together, what you end up with by doing that, the mean of the sample means, should be close to the mean of the whole population. How close? Well, the more samples you have and the bigger those samples are, the closer it should be. Okay, second thing it tells us, the standard deviation of the sample means is sigma divided by the square root of n. So the standard deviation of those sample means, that's going to measure how much they vary from each other and from the population mean, how different they are from one another and from the mean of the whole population. That standard deviation of the sample means it should be less than the standard deviation for the whole population, the standard deviation for the heights of the individual flowers. And in fact, it should be equal to the standard deviation of the population divided by the square root of the sample size. That's what that letter n stands for, the sample size. How many flowers are in each sample? And the third thing this tells us, the x bars, the sample means, will be normally distributed provided the samples are large enough. So even if the data values for the original variable are not normally distributed, the sample means will be. So imagine we had a meadow full of flowers, but the heights of the flowers did not follow a normal distribution. Instead, all of the flowers were either exactly 3 inches tall or exactly 7 inches tall. So it had to be one or the other. They weren't all spread out in a nice bell curve. I could still ask you to go out and get a sample of flowers. Go out and pick a dozen flowers at random. Some of them would be 3 inches tall, some of them would be 7 inches tall, and when you average those 12 heights together, each one of which is either 3 or 7, the average you get, that's the sample mean, might come out to be 5 if you have exactly the same number of 3s and 7s in your sample. Might be a little less than that, like 4.667. Might be a little more than that, like 5.333. But different samples would have different means, and all those different sample means would at least approximately follow a normal distribution. And it would be even closer if you had bigger samples. Like instead of just 12 flowers in each sample, if you had 40 flowers in each sample. Everybody pick a sample of 40 flowers, calculate the sample mean, and then look at all those different sample means for all those different samples of 40 flowers. Some are more than 5, some are less than 5, some might be exactly 5, but they would follow a normal distribution. If you graphed them out, plotted your data, they would follow something that looks pretty close to that bell-shaped curve. That's the shape of our normal distribution. Okay, now that I've given you kind of the theoretical background to what's going on in this section, let's go and talk about how we actually solve the kinds of problems we'll be solving. And that kind of problem is, given a sample that is not a randomly selected individual, but a randomly selected group of individuals, we want to know how the sample mean will compare with the population mean. And so the problems in this section are similar to the last section, except that they're questions about sample means rather than individual values. So when we write them in probability notation, they won't be P of X something, like the probability of X being greater than 17.5. Instead, they will be P of X bar something, the probability of X bar being greater than 17.5. And so what we will do differently is, if you do this by finding z-scores and working with those, the formula that you use to convert to z-scores looks like this. Z equals X bar minus mu over not just sigma, but sigma divided by the square root of n, because that's the standard deviation of the X bars. Now, if you put this into your calculator, remember you're going to need parentheses around both the numerator, the X bar minus mu part, and the denominator, the sigma divided by the square root of n part, so that it evaluates everything in the correct order. And if you're using a graphing calculator function like normal CDF or an app or something like that, it works a lot like the examples we were doing in the last section, except that when it asks you to put in a number for the standard deviation, the number you put in should be sigma divided by the square root of n. It should be the standard deviation for the original individual population divided by the square root of the sample size. Remember, n stands for how many flowers or people or whatever you have in your sample. So let's go back to this example question. I'm going to stop this video here and come back in the next video when we have plenty of time to work through this, and I'll show you all the different ways you can do it. You can use the method where you calculate the z-score yourself and look it up on that table. You can use a graphing calculator or other apps or software. So we'll go through all the ways we can do this in the next video.